With more than 5,000 commercial aircraft in operation and thousands more on order, the United States sits at the center of one of the most complex manufacturing industries ever created. Modern airplanes are not just vehicles, they are flying systems built from millions of individual parts, sourced from global supply chains, assembled inside buildings so large they feel like indoor cities. But here's the part very few people know. A single large aircraft can contain more than 2 to 4 million components, over 400 kilometers of wiring, and systems so complex that no single company builds everything alone. Instead, these machines pass through giant factories, precision machining plants, composite fabrication lines, and final assembly facilities that operate at an industrial scale few people ever see. This creates a massive hidden industry. Mega assembly lines, robotics, high-precision engineering systems, and global logistics networks working together to turn raw materials into machines that can fly across continents. Today, we're stepping inside the supergiant aircraft factory, where America builds flying machines with millions of parts in one of the most advanced manufacturing processes in the world. Airplanes might look simple from the outside, a long body, 2 wings, engines underneath. But inside, they are among the most complex machines ever built. A single commercial aircraft must handle extreme pressure differences, high-altitude temperatures, turbulence forces, long-distance fuel efficiency, and passenger safety requirements all at once. That means every part, from the largest structural beam to the smallest electrical connector, must be designed, tested, and assembled with precision. In the United States, companies like Boeing produce aircraft that cost anywhere from $80 million to over $400 million per unit, depending on size and configuration. But airplanes don't begin in one factory. They begin across an entire industrial network. The journey starts with raw materials. Aluminum alloys, titanium, carbon fiber composites, high-strength steel, and advanced polymers are produced in specialized plants. These materials are chosen for strength, weight reduction, corrosion resistance, and durability. From there, they are shaped into components. And this is where the scale becomes impossible to ignore. Across multiple facilities, giant machines cut, form, and machine parts that will eventually become sections of the aircraft. Wing panels are built from layered composite materials baked in massive autoclaves. Fuselage sections are formed into cylindrical shells large enough to walk through. Landing gear components are forged from high-strength metals capable of supporting hundreds of tons. Each section may be built in a different location. Some parts travel hundreds or even thousands of miles before final assembly. This is not a single factory, it is a distributed manufacturing system. Once major components are complete, they move toward final assembly. And this is where the industry becomes truly mind-blowing. Inside final assembly plants, aircraft sections arrive by truck, rail, or specialized transport aircraft. One of the most famous examples is the giant assembly buildings, where entire planes are constructed from modular sections. The first phase begins with the fuselage. Large cylindrical sections are aligned and joined together to form the main body of the aircraft. Precision tools ensure alignment within extremely tight tolerances. Even a small misalignment can affect performance. Once the fuselage is complete, the wings are attached. This step requires massive lifting equipment. Cranes carefully position wings weighing several tons each, aligning them with the fuselage structure. Bolts, fasteners, and structural joints are installed with exact precision. Then come the engines. Modern jet engines are among the most powerful machines ever built. Each engine can cost tens of millions of dollars and must be installed with exact alignment. Technicians connect fuel systems, electrical systems, and control interfaces. After that, the aircraft begins to look complete. But the real work is still ahead. Inside the fuselage, teams install systems that passengers will never see. Miles of wiring are routed through the aircraft, hydraulic systems are installed, environmental control systems regulate air pressure and temperature. Avionics systems are mounted in the cockpit, control surfaces are connected. In total, a single aircraft can contain over 400 kilometers of wiring and thousands of sensors. This phase is often the most time-consuming, because every system must be tested and verified. Then comes the cabin. Seats are installed, overhead bins are mounted, lighting systems are connected, galleys and lavatories are fitted, interior panels are attached. At this stage, the aircraft begins to resemble the plane passengers will eventually board, but it still cannot fly. Before any aircraft leaves the factory, it must pass a series of inspections and tests. This is where the manufacturing process becomes even more intense. Technicians run system checks across electrical, hydraulic, fuel, and control systems. The aircraft is pressurized on the ground to simulate high-altitude conditions. Sensors monitor for leaks, stress, and performance issues. Then comes taxi testing. The aircraft moves under its own power for the first time, testing braking systems, steering, and engine response. Finally, the aircraft enters flight testing. Test pilots take the plane into the air, evaluating performance, handling, system behavior, and safety under real conditions. Only after passing all required tests does the aircraft receive certification for delivery, and even then, the process is not finished. Airlines may customize interiors, branding, seating configurations, and onboard systems before the plane enters service. From start to finish, building a large commercial aircraft can take months to over a year, depending on production schedules and complexity. The scale of the operation is enormous. Some assembly buildings are so large they can fit multiple wide-body aircraft at once. Production lines move slowly, with aircraft advancing through stages like a moving city of machines. But behind the machines, human expertise remains critical. Engineers design systems, technicians assemble components, inspectors verify safety, logistics teams coordinate parts arriving from around the world. Maintenance crews ensure equipment runs without interruption. Without this coordination, the entire system stops. Technology is also reshaping the industry. Robotics assist with drilling and fastening. Digital models simulate entire aircraft before physical assembly begins. Sensors track performance during production. Data systems monitor every part from origin to installation. This level of control is necessary because the margin for error is extremely small. A mistake in one component can affect the entire aircraft. That is why precision defines everything. And perhaps that is what makes this industry so fascinating. Most people see an airplane as a single machine, but in reality, it is the result of millions of parts, thousands of workers, and one of the most advanced industrial systems ever created. And it all comes together in a single machine capable of crossing the planet. Inside the supergiant aircraft factory, America does not simply build airplanes. It builds some of the most complex machines ever created. If you enjoyed this deep dive into one of the world's most advanced industries, make sure to like, subscribe, and hit the notification bell so you never miss our next exploration into the giant systems powering modern life. Thanks for watching. Every single day, in massive factories across the United States, machines so large they can carry 400 tons in a single load are being built from the ground up. These are not ordinary vehicles. These are mining trucks, giants of steel and power that move entire mountains, one load at a time. But here's the part most people never see. Before these machines ever reach a mine, They begin as thousands of individual components, assembled with extreme precision in some of the most advanced heavy equipment factories on Earth. Today, we're stepping inside the supergiant mining truck factory, where 400-ton monsters are engineered, built, and brought to life in a mind-blowing industrial process. Before we dive in, don't forget to like, subscribe, and turn on the notification bell so you never miss our deep dive documentaries into the industries that power our world. The story of mining trucks begins long before the first piece of steel is cut. It begins with demand. Around the world, mining operations move billions of tons of material every year: coal, copper, iron ore, gold. To keep up with this scale, companies need machines that are not just large but incredibly efficient. That's why mining trucks have grown to extraordinary sizes. The largest models can carry up to 400 tons of material in a single load. To put that into perspective, that's equivalent to the weight of more than 200 cars, all transported at once across rugged terrain in extreme conditions. But building a machine like this is no simple task. It starts in the design phase. Engineers spend years developing each model, using advanced simulation software to test structural strength, weight distribution, and performance. Every component must withstand constant stress, vibration, and extreme temperatures. A single truck contains tens of thousands of individual parts, each designed to work together seamlessly. Once the design is finalized, production begins with one of the most critical elements: the frame. The frame is the backbone of the entire truck. Inside massive fabrication shops, thick steel plates are cut using high-precision plasma and laser systems. These plates can be several inches thick, designed to handle enormous loads without bending or cracking. The pieces are then welded together, and this is not ordinary welding. Robotic systems and highly skilled welders work together to create joints that must endure years of heavy use. Some welds stretch several meters long, and everyone is inspected using ultrasonic testing to detect even the smallest flaw. Because in a machine of this size, even a tiny defect can lead to catastrophic failure. Once the frame is complete, it moves to the machining stage. Here, critical mounting points are milled with extreme precision. Bearings, axles, and suspension components must align perfectly. The tolerances are tight, often within fractions of a millimeter. Next comes one of the most powerful components of the entire truck: the engine. Mining trucks are equipped with engines producing between 3,000 and 4,000 horsepower. These engines are assembled separately in specialized facilities where technicians build them piece by piece, installing pistons, crankshafts, turbochargers, and fuel systems. Some trucks use diesel-electric systems. In these designs, the diesel engine doesn't directly drive the wheels. Instead, it generates electricity, which powers electric motors connected to the wheels. This system provides smoother power delivery and better efficiency under heavy loads. Once the engine is complete, it is carefully installed into the truck's frame using massive cranes. The next stage is the drivetrain and suspension. Unlike regular vehicles, mining trucks must handle extreme weight while traveling over uneven terrain. The suspension systems are designed to absorb massive shocks, while axles and drive systems distribute power evenly. Then come the wheels. And this is where the scale becomes truly unbelievable. Each tire can stand over 4 meters tall and weigh several tons. These are among the largest tires ever manufactured. Installing them requires specialized equipment. Workers use hydraulic lifts and precision tools to mount each wheel onto the truck. Even a single tire can cost tens of thousands of dollars. With the major mechanical systems in place, the truck moves to the electrical and control system stage. Modern mining trucks are not just mechanical, they are highly intelligent machines. Sensors are installed throughout the vehicle to monitor performance, temperature, load weight, and system health. GPS systems enable precise navigation within mining sites. Some trucks are even equipped for autonomous operation. This means they can drive, haul, and dump material without a human driver, following programmed routes and responding to real-time conditions. Once all systems are installed, the truck undergoes final assembly. The dump body, the massive container that holds material, is mounted onto the frame. Hydraulic systems are connected, allowing the truck to lift and unload its cargo. At this stage, the truck begins to resemble the giant machines seen in open-pit mines. But it's not ready yet. Before any mining truck leaves the factory, it must pass rigorous testing. Each system is checked. Engines are run under load, brakes are tested for reliability, hydraulic systems are pushed to their limits. Some factories have dedicated test tracks where trucks are driven under simulated working conditions. Only after passing all tests is the truck approved for delivery. Transporting these machines is another challenge entirely. Because of their size, mining trucks are often shipped in parts. Frames, engines, wheels, and dump bodies are transported separately to mining sites, where they are reassembled on location. Once assembled, the truck begins its real job. In open-pit mines, these giants operate 24 hours a day, moving massive amounts of material. A single truck can complete multiple cycles per hour, hauling hundreds of tons each time. Over the course of a year, one truck can move millions of tons of earth and rock. This level of productivity is essential for modern mining operations. But what makes these machines even more impressive is how they are evolving. Automation is becoming increasingly common. Autonomous mining trucks are already operating in some of the largest mines in the world. These vehicles use advanced sensors, radar, and artificial intelligence to navigate without human input. They can optimize routes, reduce fuel consumption, and operate continuously without fatigue. This represents a major shift in how mining is done. From manually operated machines to fully autonomous fleets, the industry is moving toward greater efficiency and safety. Back in the factory, production continues non-stop. Teams of engineers, technicians, and workers collaborate to build each truck. The process is complex but highly coordinated. Every component, every system, every detail must meet strict standards. Because when these machines enter service, they operate in some of the harshest environments on Earth. Extreme heat, freezing temperatures, dust, vibration. And yet, they must perform reliably, day after day. From raw steel to a fully assembled 400-ton machine, the journey of a mining truck is a testament to human engineering and industrial capability. It's a process that combines strength, precision, and innovation at an incredible scale. And it's a process that powers industries around the world. Because without these machines, modern mining would not be possible. No metals, no energy resources, no infrastructure, just untapped materials buried beneath the earth. If you enjoyed this journey inside the supergiant mining truck factory, make sure to like, subscribe, and hit the notification bell so you never miss our next deep dive into the industries that shape our world. Thanks for watching. Smaller than a fingernail, thinner than a piece of paper, yet powerful enough to run everything from smartphones to satellites. Welcome to the supergiant computer chip factory, the beating heart of modern technology. Here in America, inside billion-dollar clean rooms where even a speck of dust could ruin everything, sand is transformed into intelligence. Silicon becomes the brain of the digital age. Before we dive deep into this breathtaking world of atoms, lasers, and liquid light, subscribe and turn on the bell, because today we're taking you inside one of the most advanced manufacturing facilities ever built by humankind. This is not just a factory, it's where the future is born. It all started with sand, more precisely, silicon, one of Earth's most abundant elements. In the 1940s, American scientists discovered how to